Yes, sorry. Okay. Hi everyone. Hi. Hi. Okay, is there any question about previous session? If there is any question, please ask me. No? By the way, why don't you watch and study the tutorial sessions? I believe about 20 to 30 people only have watched it. And the class is 109 students. So the tutorial sessions are complementary to the actual lectures, and we cover important things in them, including coding, right? And you need coding also. But
just wondering, for the tutorials or review of Python code, will we be implementing that code in our assignments or projects?
So soon I'll try to post your assignment one, hopefully. Depends on how fast I can do that. But you will have coding question. You will have manual solution question too. Also, for your project, you need to code, right? Therefore, tutorial sessions are important. I believe not all of them will be coding, but many of them will have coding. And for example, the plan, this is the plan that so many of the materialistic optimization algorithms that we are covering, you will see their codes in the tutorial sessions. Also, you will see some examples. And for example, one of the tutorial sessions will also talk about I think solving traveling salesman problem using ant colony algorithm. So this is at least the agenda that we are having in mind. So there are several questions that you will see, and I believe they are important. So as I also requested you in Learn to please watch and study the tutorial sessions, please do so. Thank you. And also, I encourage all of you guys to participate in the class. I see that the population of class is decreasing gradually, and I think it's not a good sign. But please come to the class and also ask questions. I believe the best way that you can understand is participation in the class. And any question? No? Okay. So what did you cover so far? We covered preliminaries of optimization, and then we talked about local search and its variants, including iterative local search, guided local search, VNS, GNS, and then we moved to simulated annealing. And so the local search backbone idea, so every algorithm that we are introducing has some important idea behind it, right? For example, local search is the backbone of almost all materialistic optimization algorithms, because most of them have local search in them. And also simulated annealing's idea was accepting worst candidate solutions too, right? Giving a chance to also not perfect candidate solutions in order to explore. Otherwise, we just exploit and we get stuck in the local best, right? Then we covered particle swarm optimization. What was its main idea? Let's use several particles, several candidate solutions, which collaboratively or cooperatively try to find the global best. And then we also covered genetic algorithm, which also tries to use several candidate solutions, but models them as chromosomes, and these chromosomes can have crossover and mutation. And I told you that in genetic algorithm, crossover plays the role of exploration, and the mutation plays the role of exploitation. But I also said you might have combination of ideas. So you might have some variants of genetic algorithm where you can also do local search around every chromosome in addition to doing random mutations, right? So you can have in genetic algorithm, you may want to have to exploit in two ways, either both mutation and local search. And yeah, we cover different variants of these algorithms. So we have a lot of variants that we have covered in this course, right? So now let's move on to the next materialistic optimization algorithm, genetic programming. And genetic programming is also a very important algorithm, and its main idea I will tell you, and I believe it's very, very interesting. So first off, it's different from genetic algorithm, but it uses crossover and mutation, so it uses the same idea behind genetic algorithm. Hence, its name is genetic programming. But you shouldn't confuse genetic programming with genetic algorithm. Okay. So, idea and concepts. In genetic algorithm, the chromosomes, which were the candidate solutions, right, are multidimensional vectors or matrices. We saw genetic algorithm in the previous session, and we saw that it is the chromosomes are multidimensional vectors or matrices, right? But in genetic programming, guys, please focus on this because I believe this is important. The chromosomes or the candidate solutions are 3 data structures. But you might be wondering, why is it important? Let me tell you what we can do by genetic programming. Do you know regression problem or prediction problem in machine learning? For those of you who don't know, okay, regression problem is like this, that you, based on some input features, you try to predict some continuous label, okay? As an example, assume I want to learn a machine learning model for training an artificial leg for people who don't have leg, right? Artificial joint and leg. So I can go to a healthy leg and capture the EMG signals, the muscle signals, right? Which the brain gives to the joint to move. And then I can ask that person with healthy leg to move their leg with different angles, right? And for each angle, I can capture the EMG signal. Then if I can do it with fine steps, right? Then I can have a lookup table. So, for example, I can say for these EMG signal, and this EMG signal might be a vector, right? It itself might have some features. It might not be just a scalar. So, anyways, we have some features, EMG signals, and corresponding angles, right? And let the angles be labeled here. Okay. So in here now I have made a lookup table. Let's call this lookup table a data set, where the angles are the labels, right? Continuous labels. And now I train a machine learning model for regression. Regression is another name for prediction. I want to predict, okay? I learn a machine learning model to learn this lookup table, but not just memorize it. If I just if my model only memorizes this lookup table, it hasn't done anything, because any idiot can memorize a lookup table, right? So we don't want the machine learning model to be an idiot. So what should we do? The main art of the regression model, the machine learning model, is to interpolate and extrapolate this table, right? Because no matter how much fine my steps can be, still there is some gap between my angles, right? And I want the machine learning model to interpolate between the angles automatically and also extrapolate, not just interpolate, and also extrapolate outside of the range of the table, right? Then, for example, in my lookup table in my data set, I had the signals for 40 degrees and 45 degrees and 50 degrees assumed. Then I train it, so my machine learning model has trained it, and then I put it on an artificial leg, right? Then I capture in, now I'm in the test phase. The training is over, I'm in the test phase. Now the person with without any leg will have some EMG signals in their joint, right? Then I can give that EMG signal to the machine learning model, to the regression model, to predict which angle it is. Assume that the EMG signal which comes from that leg is kind of, its pattern is between the EMG signal for 40 degrees and the EMG signal for 50 degrees. It's kind of between these two. Then my machine learning model is supposed to predict maybe 43, right? Because the pattern of data was between the EMG signal of 40 and 50, and the labels of them were 40 and 50, right? So the output of this new EMG signal must be 43 around, something like that. So it means that my machine learning model could interpolate, right? So this is a regression problem. You can use that in various types of data. You can use that also in time series. So you can use regression in simple data like this, also in time series data, such as weather prediction, right? Whenever you see in the news, they say tomorrow might be rainy. Then how do they find out? So they have trained machine learning models and statistical models in order to predict, right? Also, you can predict, although the people in finance don't believe in that, but you can predict stocks, right? You can have a stock prediction, but with, of course, with a lot of error. Otherwise, many people nowadays were reached just by regression. But I'm saying that you can have a stock prediction, you can have weather prediction. Of course, when you have a time series, you have a window of your some previous data. You give that as feature, and the next day, the next output will be the predicted output, right? Okay, so I gave you examples for regression. Now, what have I done in my regression? In my regression for machine learning, I have some model, let's call it F. It gets my X as input, right? It outputs some label, agree? And this F has some parameters, theta, right? And the only thing that machine learning model does is to find the theta, the parameters of F. The whole machine learning is actually like that. If you consider this F of theta for classification, then this becomes a classification model. But now here, I'm assuming this is a regression model because regression model is more generalized than classification models. You can kind of see classification as a special case of regression, okay, where the labels are discrete and finite. But so I'm saying that the whole machine learning is trying to find parameters of the model. And we can call this model a learning model. So now what is the difference between machine learning algorithms? How to find this theta. So one algorithm says, I find this theta in this way. The other algorithm says, I find theta in another way. Also modeling the F. So you can define F to be different functions, right? Different ways. You can model F in different ways, and also how to find the parameters of this model. So these are different machine learning algorithms. For example, we have linear regression. So in linear regression, F of theta is a linear function, and we try to find the parameters of this F of theta. It can be a neural network, where in this case, theta will be the weights of the neural network, right? But now, what if consider another scenario. What if I say, I don't want to just have something like this, a model with some parameters and learn them. I want to give you some basis operators, some basis functions, okay? And then such as plus, minus, subtract, addition, multiplication, division, sine, cosine, logarithm, exponential operator, these things, right? Or these basis functions or operators can be logical operators, and, or, not, x, or the gates, the logical gates, okay? So I give you these operators or basis function, and then I say, combine these functions however you want, but find some function which fits my labels exactly as accurate as possible. So what do I mean? So do you agree that if I fit x to that with the parameter theta, it gives me y, right? In regression. In regression, I don't care much about this f. I only care about learning the parameters. Now the scenario has changed. I say I care about the expression of f. I want f to be a combination of some operators. For example, I want f to be either sine of x, so x has some dimensions, right? x1 to x2. For example, sine of x1 squared plus tangent of x2 over square root of x3. So it can be complicated, right? You can have any combination of basis functions. And so for example, here, my basis functions are sine, tangent, square root, division, plus, right? Now you have freedom to combine these basis functions differently. Also, you might have a long expression, a short expression, right? But I want you to find some expression, some function, which fits this lookup table that I have, the data set that I have, right? That whatever feature that I give to this function, it outputs a label which is as close as possible to the actual label. Did you understand what I'm doing here? Okay. So this is exactly what genetic programming does. Okay. Genetic programming is trying to fit a function to your data set. Fit a function, right? Not a black box. Usually you can see the regression like a black box. Okay. I learned that black box, I give it to you. Now fit anything that you want, it gives you some predicted output. This is in regression, right? But in genetic programming, I don't want that to be a black box. I actually want it to be a white box. I want to see the operator, the function of that model. Okay. And I think you understand why it's called programming, because we are programming, we are finding which function we can fit to our data set, right? So genetic programming, its idea, I think, is very cool. Even just its idea is very cool. Okay. Genetic programming was first proposed in 1985. Okay. So it tries to extend computational intelligence to programming and function generation. By the way, they might have named it programming also because the basis functions, operators might be logical operators. Then do you agree that you can write any logical? So you give me some lookup table of binary logics. What do I mean by lookup table? So for example, what is XOR? You tell me. X1, X2, 0, 0, 0, 1, 1, 0, 1, 1. Have you passed in logic course? Right. So its output is 0, 1, 1, 0. This is XOR. XOR of X1 and X2. Okay, assume I give you this lookup table or a very complicated lookup table, right? And then I give you some basis operators which are and, or, and not, for example. These are the logical gates. Then I say, try to fit some logical expression to this table, right? And this logical expression might be very complicated. It might be one line, its length might be one line or two lines of a lot of logical operators, right? Of course, the simpler the expression, the better it is for me. And yes. So, by the way, I also, in this sentence, I told you that chromosomes in genetic programming are trees. Can you tell me why? Can you guess why the chromosomes, the candidate solutions, or the candidate function expressions can be represented as a tree? Let me open a page. Give me some function. Oh, you were saying? So you are saying that it's because the next generation of the solutions are dependent on the previous generation. But no, we had this dependence also in genetic algorithm. But in genetic algorithm, our candidate solutions were vectors, right? The chromosomes were vectors. Here, the chromosomes are not vectors, but trees. And I want you to think why chromosomes are trees here. I can explain this to you with some simple example. Give me any function you want. Some, not too complicated, but give me. Okay, you tell me. Yeah, I think you guessed it correctly. But let me give you explain what you just said with some example. Give me any function. No, yes, some expression. I mean, not just cosine. Cosine of what? Cosine of x1, right? It can be any complicated function. Tell me, cosine of x1. Do I power it? What? To the power of 3? What? Divide is outside of cosine or inside? Outside, okay. Divided by the square root of x2. Is that enough? It can be more complicated, but I think using this, we can understand it. Okay, I want to represent this function as a tree. So first, I start from the bottom of tree for you to understand. For example, I have x1. Then I have to the power of 3. I don't know how to represent it. To the power of 3 operator. It gets x1. Okay, then let's make it a bit more complicated. Plus x3 inside the cosine. Okay, so then just give me a second to think. Then plus operator. Then I have x3. So far I have inside the parentheses. Then I give it to cosine operator. On the other hand, in the denominator, I have x2, but square root operator. Then I have, so this is numerator, this is the denominator. Then I can combine them by division operator, right? So this is the whole function f. Did you understand how I made the tree? For you to understand the tree, try to analyze it from bottom to up. So let me repeat it. I have x1 to the power of 3. So operator of power 3 is applied on x1. And it has one input, right? The operators might have one input, two inputs. So here power is one input. Then I have x3. The operator plus has two inputs, which gets x1 to the power of 3 and x3. Then cosine has one input. Cosine of them. This here, up to here, I am in the numerator. Now let's design the denominator. X2 square root has one input, right? Then I have division, and division has two inputs, numerator and denominator, right? Numerator and denominator, and this gives me a, yes.
You could provide some like visuals or some more information as to like the differences between all these algorithms, and, like pros and cons. I'm so lost right now.
So which part is that? So let me recap. So what we have done so far in the course. First, we covered preliminaries, right? And then so in preliminaries, we said we wanna optimize some cost function, right? And then we said, okay, of course we should do it by classical optimization, right? Classical optimization like first order and second order optimization. But what if my cost function is too complicated, highly non-convex, and too many constraints, for example, too complicated? Then maybe our optimization toolbox takes forever to be solved, right? Or sometimes I can't calculate gradients, right? So because for classical optimization, you definitely need gradients. If you are using second order optimization, you need both gradient and Hessian, right? So at least you need gradient. But what if your cost function is a black box? So you can just evaluate it exactly how, in the same way that you do it in reverse engineering. What do you do in reverse engineering? You have a device, you want to do reverse engineering. You can't access inside of it. You see it as a black box. You give some different inputs and see the outputs to estimate the behavior of this device, right? So likewise here, either we don't have, so here, if it is black box, of course we can't calculate the gradient because we don't have the function. So either the cost function is highly non-convex and too complicated, or it's a black box and I can't calculate the gradient. In these cases, I have to search for optimization. Then we said that we can do random search, which is awful because we may never find a solution. We can do grid search or brute force search, which is awful because of its time complexity. It takes forever, right? Then the best way is the middle case scenario between random search and brute force search, and that is intelligent search. Intelligent search is also called meta-heuristic search. Then we started covering meta-heuristic search algorithms. And I said, I'm gonna cover important meta-heuristic because there are thousands of meta-heuristic optimization algorithms, important ones which have some idea behind them, right? Some important idea. We started from local search. Why? Because local search is almost the backbone of all meta-heuristic optimization algorithms. In the loops of various meta-heuristic optimization algorithms, they usually do local search, right? So you will have nested loop in algorithms that you see. Then, so we covered the most important one, which was local search or hill climbing. Then we moved on to the next meta-heuristic optimization algorithm, and that was simulated annealing. What is the main idea behind that? The important idea behind simulated annealing? Giving a chance to worse candidates. Otherwise, we just get stuck in the local minimum. For us to also explore, let's give a chance. So we covered that. That was also an important algorithm, right? Many state-of-the-art meta-heuristic optimization algorithms are using these basic algorithms as their main ideas. They're combining them, right? I'm just giving you the most important ones. And then after simulated annealing, we covered PSO. What was the main idea of particle swarm optimization? Having several candidate solutions to collaboratively find the best solution, right? Also, we covered genetic algorithm, which tried to model the particles or several candidate solutions as chromosomes, and it used the idea of evolution, crossover, and mutation for updating the solution. Then it was until that was the end of the previous session. Now in this session, I'm starting another meta-heuristic optimization algorithm, which has another main idea, right? And this idea is what? To fit a function to my data set. You might be wondering, here I'm not minimizing anything. It's not an optimization problem, but I tell you it is. Because, as I said, do you agree that if I give you a random function, it can give me some labels still, right? But the labels might be awful. So I can calculate the mean squared error between my predicted labels and the actual labels in the dataset. So still I'm doing some optimization. I'm minimizing the error of my predicted labels and the actual label. Just in parentheses, let me tell you that all machine learning is optimization, right? All machine learning is optimization, and we usually use classical optimization in machine learning. right? But this course is not machine learning course. Otherwise, I would teach you machine learning, right? This course, I'm talking as a part of this course, I'm talking about materialistic optimization, which is a part of soft computing. This course is mostly about soft computing. And I was saying that, so here, I can model fitting a function to some data set as an optimization problem where I want to minimize the mean squared error between the actual labels and the predicted labels. Okay, now, so for this, I'm offering to you the next algorithm, which is genetic programming. And genetic programming has this main idea behind that. Even the idea, I think, can be a paper. Even the idea without how to do that is novel. The idea of fitting a function to some data. Before the proposal of this algorithm, no one had thought of this. They're always thinking to fit a black box model, such as a regression model, to some data set. Regression is very old, but fitting a function expression to data set is new. It's novel, right? Did you understand? Okay, great. Thank you. So here I'm saying that I can represent any function expression as a tree. Agree? I just showed you. And it can be very complicated. The more complicated the function, the lengthier the tree, right? The lengthier and the wider the tree. Okay. So, as I said, we can use this idea for logical expressions. So we can have, and if we have logical expressions, then the tree nodes, except the terminal nodes, are logical operators, such as and, or, not. Just recall the tree that I showed you. Do you agree in this tree? My variables are the terminal nodes, the children of the tree. These are the variables. Agree? This, and this. The rest of the tree, the rest of the nodes of the trees are just operators. Did you understand? So all nodes except the terminal nodes are variables. All nodes except the terminal nodes are operators, and the terminal nodes are the variables. Okay. So in logical expressions, the all nodes except the terminal nodes are logical operators, such as and, or, not, etc. And terminal nodes are the binary variables, 0 and 1, right? It can be used for function expressions. The three nodes except the terminal nodes are functions such as multiplication, division, addition, subtraction, sine, cosine, logarithm, etc. So here, for example, I have said addition and subtraction, but we can only have addition and negation, right? If I have addition and negation, I can model subtraction too. Terminal nodes are here continuous variables. Okay. So a tree, now let's talk about tree a bit. A tree has some nodes starting with a root node. Okay. And the node may or may not have a child, right? Or multiple children. So a node may have it. If a node doesn't have any child, that's a terminal node. Okay. The tree ends at that node. Otherwise, the node has one child or multiple children. When drawing the tree, every node is connected to its children by some lines, right? By lines. What is branching factor? The number of children at every node, tree node. So when a node has two children, the branching factor is 2. If it has one child, the branching factor is 1. We can also have the average branching factor of the whole tree by averaging the branching factors of the nodes of the tree, right? What is terminal set? Terminal set is a set of variables which are represented as the terminal nodes, right? For example, in this example, the terminal set is the set of x1, x2, and x3, right? So what is function set? Function set is a set of functions or operators which are represented as the nodes excluding the terminal nodes, right? So the operators, right? The set of operators or functions, we call that function set. In this example, what is the function set? Can you tell me? Tell me so I write it down. What are the functions used here? Tell me. No, don't raise hand, just shout it out. What? What did you say? Cosine? Power of, cubed, power of plus, square root, right? Square root. Also division. Agreed? I think that's all. Right? So this is function set. Well, we also have some semantic rules. Might or might not have some semantic rules. What are the rules for operations or functions which restrict the structure of the tree from being any structure? What do I mean? For example, we know that cosine has one input. Can cosine have two inputs? No. This is a semantic rule. Division has two inputs. Can division have one input? No. Or three inputs? No. Right? So the number of inputs per operator is one of the semantic rules. Or, for example, we can't have division by zero. That's another semantic, right? And things like this. Yes, for some operators such as plus, you might have multiple. Again, you might add this semantic rule that I want my addition to have two inputs only. Then you can model three additions with two additions, right? So what do I mean? If I have A plus B plus C, either I don't have semantic rule and I say A, B, C, or I have the semantic rule that my plus has only two inputs, then I can model it in this way. A and B, then C. Agree? Okay, what was it?
In our example, would the root node be part of the terminal or the function set?
Example of what?
In our B example, would the root node?
This example, you mean?
Yeah.
Okay.
The function part of the terminal set or the function?
No, the terminal nodes are, the terminal set has the variables only, which appear in the terminal nodes, right? So the terminal nodes, any terminal node is a subset, is a member of the terminal set, right? Also, any non-terminal node is a member of the function set, right? Okay. By the way, in a tree, maybe you don't use all of your operators, right? For example, I can increase more things here by, for example, sine, but I haven't used that here. So we might have a big function set and we use some of the operators, right? Also, likewise for the variables. For example, my terminal set might have x4 too, but here I didn't need that. Okay. When does that happen? When in your lookup table in your data set, x4 doesn't have any impact. When you optimize, you do the genetic programming iteratively, finally you find some tree like this that doesn't have an x4 in it. It basically means its interpretation is that x4 doesn't have any impact. It's kind of a random variable, right? If you can calculate the mutual information between x4, the fourth dimension of x, and the labels, the mutual information is very low. Yes. So if I want to speak in the language of machine learning, if you do feature selection, you can remove that feature x4, right? Some example trees I have shown here. One example for logic example. and another one for function example. Okay. Logic example. Assume my desired is x1, x or x2, right? And assume my function set has and, or, and not. My terminal sets are x1 and x2. By the way, here I'm assuming only I have two, right? Because I have only x1 and x2. What if the desired could be more complicated, such as x1, x or x2, and x3, something like that, right? Or you might not have the expression, you might have the lookup table. Okay. So here terminal set is x1 and x2, function set is and, or, and not, and the desired function is x1, x or x2. And according to if you have passed any course in logic, x1, x or x2 can be written in this way: x1 and x2, or not x1, x or, I think this must be or, sorry, or, yes. Give me a second to think. No, this is and. Yes, and not x2. Okay. If you write the lookup table, you can find that. And what is XOR, by the way? I wrote it once here. 0, 0, 0, 1, 1, 0, 1, 1. XOR of these two is 0, 1, 1, 0. XOR basically means, in simple words, that I want only one of them to be 1. So this or the other one, but not both. Yes. So I'm saying that the function set are just valid operators that you are allowed to use. Yes. Yes, if you had XOR in your function set, then the solution would be trivial. Okay. Yes. What? Which one is the lookup table is exactly opposite, or you mean it must be this? I might be wrong, so let me check. XOR logic. No, I was right. What? Which function are this one, you mean? Oh, sorry. This one? Okay, just give me a second. Do you mean that there should be a not here? Okay, sorry about that. Sure, I will correct the slides, but so what I wrote in the lookup table is correct. XOR is short for exclusive OR. It means that only one of them should be 1, not both of them. Okay, and apparently that my expression here was wrong, and it needs a not at the end. Okay, that's fine. By the way, you can check out whether this equation is correct or not, and I think one of you guys just checked and found out that there was a mistake here. Okay, so semantic rules, we have the operators and or have 2 inputs, right? And the operator not has 1 input. This is my semantic, right? Then what can I say? I can write this expression in this way: x1, let's implement this, x1 and x2. So I have and x1 and x2, right? Guess that. Then also let's go into this. I have not of x1, not of x2, then I have and of them, then between them I have or, and at the end I have a not, which I just need to add right now. Did you understand? Agreed? Okay. Thank you for correcting me. I appreciate it. So Also, now consider this function. Y, which is the label, equals x natural logarithm of a is also a variable, plus sine of z, z is variable, over exponential operator of minus x, x is a variable, minus 1.5. And the terminal set, of course, x, a, z, 1.5 minus 1, right? Function set, multiplication, division, plus, minus, natural logarithm, exp operator, sine, okay? Then let's write it down. So what should I do? By the way, the variable, the terminal nodes, I usually put them in a square. The rest of the nodes, a circle, right? Yes. What's the point of this, you mean? So the question is, what's the point of representing the expression as a tree? We'll see that, because we're going to use that in genetic programming. We haven't yet started genetic programming. It's the preliminaries of genetic programming. Okay. So I'm just showing you how I can show any candidate solution in genetic programming. Any candidate solution is just a function expression. Okay. So here, now let's represent this. So I have x. Let me do this. X, natural logarithm of a. Then I have multiplication between them. Agree? Now let's focus on this part. So I have sine of z, right here. Then I have also in the denominator, I have minus x first. Minus x is here. Then I feed it to exponential operator. Then between them, I have division. Then I have minus 1.5. So I'm here now. What is this here? You tell me. It's this expression, right? What is this point here? Here. I have plus between them. Agreed? Okay. Now, genetic programming algorithm. Goal of genetic programming, we have a data set, also called the truth table, right? Where every row has the input values and the corresponding ground truth label or output value. Like it's called data set, right? The goal is to find an expression of functions or operators, of basis functions, I mean, which fits to this table and can predict the labels as accurate as possible. It is similar to regression or classification problem in machine learning, where we fit a learning model to predict as desired. Okay. However, the big difference is that genetic programming finds an expression, combination of functions or operators to fit the data set. But machine learning only learns some parameters of the model to fit the data set. Okay. In machine learning, in other words, my function is fixed. My parameters are tunable. For example, the function might be a neural network. The function might be a linear function, then in linear regression. The function is fixed. So in machine learning, let me add, function is fixed. Parameters of function are learnable, are tunable. Right? However, in genetic programming, the function itself is tunable. It's not fixed. Okay. Now, initial trees. Okay, as the first stage of genetic programming. For generating every initial chromosome or candidate solution, we select a random root node from the function set, right? We get a random root from one of the operators. Then, for generating the initial trees, chromosomes, for every node, for every operator, we first decide whether it is a function node or terminal node. So I'm growing the tree. At every stage of the tree, I can randomly decide whether I terminate that part of the tree there and let it be a variable node, or I want to continue and let it be an operator node, right? Okay. And I can decide it randomly because I'm just random initialization. This is random initialization of the candidate solution. So in genetic algorithm, our random initialization was easy. We had random vectors as candidate solutions. Here we need random trees. Okay. If the depth at that node has reached to the maximum depth, so we have a maximum depth, we don't want to go forever, right? It must be a terminal node. Then if it has reached its maximum depth at that depth, then we stop that node and let it be, it must be a variable set. Otherwise, we randomly choose whether it's variable node or an operator node. If the depth at that node has not reached the maximum depth yet, we have a probability P, which is between 0 and 1, for whether the node is a function node or a terminal node. And this P probability is a hyperparameter. So, of course, the probability of being a terminal node is 1 minus P. Right? Clear? Now, for every node, we can let the branching factor be also a random variable with Poisson distribution. Poisson distribution. First off, what is Poisson distribution? Have you heard of that? So, have you heard of Gaussian distribution? Gaussian distribution is the most famous distribution for continuous variables, right? Now, what if the variable is discrete? The most famous distribution for discrete random variables is Poisson distribution. Okay? And it's this. So here, why do I need my distribution to be discrete? Because branching factor is integer. 1, 2, 3, branching factor, right? It's a discrete variable. So I can let the branching factor also be random, and I can draw this random variable from some distribution. Let it be Poisson distribution. Poisson distribution has some parameter lambda. So B is my random variable, right? And this in the denominator is B factorial. In the numerator, I have lambda to the power of B, e to the power of minus lambda. This is the expression for Poisson distribution. If you want to know how it looks like, let's go to Wikipedia. This is Poisson distribution. As you see, here my K is B, right? Branching factor. And as you see, these are discrete. With different lambdas, let me zoom. With different lambdas, you have different behavior of this distribution. Right? Okay. Let's go back to where we, okay, so here the random variable B is non-negative integer and lambda is positive. In Poisson distribution, lambda is positive. It's the hyperparameter of the distribution. For example, we can set lambda to 3, for example. Now let's analyze lambda. The larger the lambda, the larger the mean of the distribution. Let's go back to our figure. See, when I increase lambda, the mean of the distribution, like, is increased, right? It's shifted toward right. So it means that, what do I mean by this? By increasing lambda, it is more probable to get larger values for branching factor, right? So the more probable it becomes to draw larger integers. It means that if I want my tree to be wider, then I need to set lambda to be a big number. If I want to be a deep tree, not wide tree, so it means a deep tree has small branching factor, right? Then my lambda should be small. Yes. Yes. Why do I need to generate random tree? Because I need to initialize my candidate solutions randomly, right? Yes.
The second line. So talk about generating initial chromosome in its solution.
Yes.
Select a random root node function set. And then you talk about for generating the initial trees, you decide whether it's a function node or a terminal node.
No, the whole thing is together. So for this slide is one thing, not two things. There's one thing, how to generate the random initial trees. So I'm saying that for generating random initial trees, you first need a random root node.
But then you have to decide whether it's a function node or terminal node. I thought the function set by definition doesn't have terminal nodes in that.
Yes, so I'm saying that. Okay, forget this slide and listen to what I'm saying. I want to generate a random tree. Okay, initially my root node must be from the function set. I take randomly one of the operators from the function set as the root. Okay, then I draw some branching factor for that random for that root, right? And this branching factor is also random. Then I will have some children of this root. For each child, I decide whether it randomly whether I want that to be a terminal node or an operator node, right? Randomly with probability p, right? And then so I can grow the tree randomly, right? Sometimes I stop, sometimes I grow that part. And also for every node, if I decide randomly that it is an operator node, so then I choose one of the operators for that node randomly again. So everything is random. Root node is random. Operator nodes in the between of the tree are random. Whether a node is a terminal node or operator node is random. Branching factor is also random. Everything's random. Right? Agree? Yes. Determine what? The branching factor says how many operators how many children every node can have. Of course, it might be restricted by the semantic rules. So if an operator can have only 2 nodes, then I set the branching factor to 2. I don't randomly select that. But some operators might not have any semantic rule for the number of inputs, right? In this case, I let the branching factor to be random. Yes. For P, like whatever. The P, you mean the probability of? No. The probability P is just a uniform probability. Yeah. These are different. So as I'm saying, everything is random here with different ways, right? And by the way, branching factor is random if there is no semantic rule for that operator. Yes.
Is the depth like of the parameter that we set initially, or is that also just
The depth,
yeah,
the maximum depth, you mean, right?
yeah, can we set the maximum depth?
We usually set that. You usually set the maximum depth because we wanna restrict the space. Otherwise, we'll have maybe memory error to go forever.
When we have terminal node, are we just like you have the chance of having one of your variables in the terminal set appear multiple times, right?
Yes, that doesn't matter. We can have repeat. We can repeat one variable. For example, when x1 goes to sign, who says that x1 can't come to the denominator? Who said that? I can't use x1 twice, 3 times, right? Yes. Guys, please. By the way, sorry. I can use one operator also several times. I can use sign several times in my expression. Yes. No, it needs to be predefined. The user should give that. For example, the user says, I want the genetic programming to find an expression of these basis operators. Right? By the way, there are a lot of variants that you can define. For example, if you want to code, maybe the simplest variant is that you set the branching factor to be fixed. So these are variants in your hand. Do you want B to be random or do you want it to be fixed? Right? So, okay, these are the things. By the way, you can also adapt lambda. The more you go down, you decrease or increase your lambda. Or you can also adapt your P. Of course, initially, your P was the probability of being
a function node, right? Of course, initially at closer to the root, P should be you don't want to have very short trees, right? P should be bigger. Then gradually, when you go down the tree, you can decrease P because you don't want to go forever, right? So you can adapt these things to adapt P, lambda, etc. Guys, please, if there's any question, ask me, please. Okay, so every tree structure, that is every combination of functions and operators, has some fitness or cost value. Agreed or not? So I have the function expression. I have n data points in my data set. I have n rows in my data set, right? I can feed any of these to my function to get the predicted output, right? Then I can compare the predicted output with the actual output, with the actual label in the data set. So this is exactly, in this slide, I'm explaining how to calculate the cost or fitness for every tree. So for a tree structure, the cost value or the fitness, doesn't matter, can be calculated as the following. Assume the data set has R instances. So R rows, for example, right? R instances x1 to xr, where each x is a vector, right? Has some features. Agree? And the ground truth labels are y1 to yr. Here, the ground truth labels are scalar, meaning that my function's output should be scalar. You can make it more complicated. Maybe you can make functions which output vector. It becomes a bit complicated, but still you can do that, right? Every data instance xi has d features, and I denote the features by xij. Xij is the jth feature for xi, for vector xi. Did you understand? I goes from 1 to r. R is the number of data points, and d is the the dimensionality of data points, the number of features. Every tree structure, is it clear to you what I mean? Consider an Excel file, CSV file. Then you have rows and columns, right? So assume you have D columns and R rows and one column at the end. These columns are y1 to yr, the labels. Here I have x11 until x1d. Here I denoted by xr1 until xrd. So these are the features, d features, r data points, and also for each of them I have a label. It's just okay. X's are vectors, right? So that's why I have put them as bold small case. Bold small case in my slides mean vector. Non-bold small case means a scalar, right? Okay, so every tree structure represents a function expression where the variables of the function are all or a subset of the d features. We in a function expression, we might use all of the features or some of the features, right? Okay, we feed every instance of dataset x1 to xr to that function expression. Assume I have some function expression, I want to calculate its cost. I have a tree or a function expression, I want to calculate its cost. How do I do that? I feed every vector to that, and I will have outputs, predicted outputs. So I will have R predicted outputs. Agree? Then I also have R actual labels. So then I can calculate the mean squared error between them. This is mean squared error, right? Yi hat means the predicted output of that tree for the xi, for the ith data. Yi is the actual or ground truth label for the xi. So I can calculate the mean squared error between them. This can give me the cost. Now the whole idea is to minimize this cost. So what is my optimization variable here? 3. Every optimization variable is a 3. And do you understand how cool it is? Because so far in this course, our optimization variables had similar dimensionality. For example, if my optimization variable was d-dimensional, all candidate solutions were d-dimensional, right? Here in genetic programming, they might have different dimensionalities. They might have, one of them might be long tree, one of them might be a short tree, one of them might be a wide tree. The number of nodes might differ between the trees, right? So even the dimensionality of the optimization variables are different. That's very cool. Okay. Oh, by the way, so yeah, dimensionalities of trees might differ. Also, if the number of instances in the dataset is too large, where R is much greater than 1, we can use a subset. So we can randomly sample the dataset and use just a subset of the rows. Did you understand? Rather than the whole dataset. Yes. Yeah. No. So the question is, so what's the art of this? You're just making random functions and say, no, it's not random search. It's intelligent search. We are gonna use crossover and mutation on them. No, initially it's random. Genetic algorithm, initially it's random. PSO, initially it's random. But then it becomes intelligent because they collaborate with each other. The particles move toward the global best, right? It's not random. Otherwise, you're questioning the whole philosophy of materialistic optimization. The materialistic optimization just initially is random. In every step, it might have some randomness, but it is intelligent. Do you understand? Okay.
How do we use the cost to determine which one should mutate, or like which one should be cut off?
So I think you can guess what we are gonna do. We have trees. The trees, a bunch of trees, right? The trees have different costs. One of the trees might be better than the other one, right?
We cut off the bad.
So of course we'll have natural selection, and the bad ones will die without having any offspring. Okay, so the idea of genetic algorithm is used here, but for trees, yes. Please be louder. You can use other loss functions, but mean squared error is usually used for continuous labels, right? Because here labels are continuous. Yes.
The whole every data instance xi has b features.
Yeah.
Explain like what that means specifically in terms of like the ground truths and how you calculate that mean squared error.
Consider a CSV file or Excel file like this. I have R rows. I have d plus 1 columns. I assume the last column is a label.
So how do you use that to bring that mean squared error?
No. This is given to me by user. So basically, what does user give? So I have a genetic programming algorithm. What does it take as input? It takes the data set as input. It takes the semantic rules as input, the function set and terminal set. It takes all of these as input. Do you understand? So this is given.
Then in that case, where the d column represents from x1 to xd is where that actually represents.
It can be any feature. It can be any feature. For example, it might be even the data set of weather. For example, in data set of weather, assume I want to fit a function to the data set of weather, but not in a time series way, in a simple way. Okay. Assume my label is a temperature of tomorrow, but one of the features is the pollution of today, the amount of pollution. The second one is the longitude. The third one is latitude. The fourth one, just these are features. Did you understand?
So that that basically.
It's given. It's given. So in companies, I don't know if you have worked in industry or not, in companies, at least in bigger companies, we have teams. We have a data engineer team where they collect data, that they prepare the data set. We also have machine learning engineers, machine learning scientists, and these things. In smaller companies, one person should do all of these, right? So
We create a test set later as well to like evaluate our genetic or like algorithm that we create.
you can have a test set. So if you have a test set, after finding the best tree, then you can find out its mean squared error, right? On the test set, I mean. So we are going to use the operators, the different things that we had in genetic algorithm, hence the name genetic programming. Okay, so for crossover, what can we do here? In genetic algorithm, we had vectors. We could use 1 point crossover, 2 points crossover, and different ways, right? Here, what should we do? We just give me a second. We use so we agree we can transplant. When I have 2 trees, I can cut one of the trees and put it on the other tree and concatenate them. This is called transplant, right? In farming. Okay, this is exactly what we are gonna do. So I have 2 trees. I cut them in some point, like here. I cut it from here, and the other one cut it from here randomly, right? Then I take, for example, this part from parent 1 and this part from parent 2 and put this here. So I concatenate. So this comes here, right? And this came here. I can do the other way around to make the next offspring. So I can have 2 offsprings, right? I can take this part and concatenate it to this. Right? So it's very cool. It's very cool. I could transplant the trees together to have crossover. Yes. It depends on the data set. So the question is whether does it take a long time for finding the best solution? Of course, the more you search, the better solutions you might find. So you can have a maximum number of iterations, and there is a trade-off between the speed and the accuracy. Yeah. By the way, if you have training and test sets, if you only have one data set, then you can go forever and find the best tree, right? But if you have training and test sets, you probably don't want to go forever. You don't want to find the perfect tree. Why? In machine learning, it's called overfitting. You don't want to overfit to your training data, right? If you overfit, you find the perfect tree for your training data, you might perform poorly on your test data. I think it's intuitively obvious.
What is algorithm? Oh, want to transplant this part of this tree to this other part. Because in my mind, if it's done randomly, it could actually different orders.
It could make them so. You could ask the same question in genetic algorithm. In genetic algorithm, we had 2 vectors. We had 1 point randomly 1 point crossover. Do you agree? But the question is, what if the offspring is becomes worse? If the offspring becomes worse, it will die in the next generation. It will not be selected by natural selection. So again, we have different variants. So the question is, what if? So the parents might be very good, the offspring might be very bad, but the parents are already don't go to the next generation, and the offspring will also die. But it depends on which variant of algorithm you are using. Some variants of the algorithm also bring some of the good parents to the next generation. Depends on what you do. Some variants might say only good offsprings go to the next generation. Some variants might say, okay, consider all offsprings and parents together and just bring the best ones among both parents and offsprings to the next generation. Right? Okay, so crossover for genetic programming is over. Now, mutation. Mutation. For mutation, what can we do? By the way, and did you understand what this crossover is actually doing? For example, one of the trees was representing sine of x1 over square root of x3, for example. And the other one was cosine of x2, assume. Then the offsprings become something like that. Sine of, let me think. Okay, cosine of x2 over tangent of x4. Okay. Then the offsprings becomes, one of them becomes cosine of x2 over the square root of x3. The other one, for example, becomes sine of x1 over tangent of x4. Something like that. When you do the transplant, you will have the permutations of the operators, right? Interesting. Okay, so mutation. We can do function. We have various ways to do mutation. Function mutation. We replace one or several function nodes with other functions in the function set randomly. So consider some of the function nodes, which are not terminal nodes, right? And randomly replace them with one of the operators functions. Of course, when you are doing that, you are also considering, always you are considering the semantic rules. Of course, you shouldn't replace division by cosine, because division gets 2 inputs, cosine gets 1 input. You are careful about that. Also, terminal mutation. We replace one or several terminal nodes with other variables in the terminal set. So basically, we can replace the function nodes, we can replace the terminal nodes, right? For example, by replacing terminal node, I replace x1 randomly with x4, right? We can do it. Also, we can have swapping mutation. What do I mean? For the functions sensitive to order, some functions are sensitive to order, such as division. Division is sensitive to order. Then we can swap their subtrees. For example, consider this, F1, its left child is x1, and the right child is this subtree. I can swap them. I bring this to the left child and make this right child, right? Basically, if, for example, if F1 was division here, basically this mutation is having reciprocal of the fraction, right? We can have truncation or pruning mutation. What do I mean? We consider a subtree in the tree, we remove it, and we replace it with a random terminal node from the terminal set. This is pruning, right? We prune the tree. Exactly how we do it in farming, right? In gardening. So we pruned that. Okay, so we took this and replaced it with x4. We can have growing mutation. What do? We consider a terminal node in the tree and grow it with some other random functions from the function set and random terminal nodes from the terminal set. So what do I mean? Consider one of the terminal nodes, such as x2 here, right? Then grow the tree from that terminal node. So you will have a subtree there where the operator nodes are random and terminal nodes are also random, right? We can have permutation of terminal nodes. What do I mean? We permute some or all of the terminal nodes randomly. We can permute the nodes, right? For example, x1, x2, x3, we can make them x2, x1, x3. We permute them randomly. Permute all of them or some of them. We can have editing mutation. It's becoming cooler. It's very cool. See, what does it do? Whenever we see a subtree which we know is not useful, okay? Sometimes it's so we might have prior knowledge, right? Sometimes we have prior knowledge. For example, the user knows that maybe some function expression, some sub-function expression, I mean, is not useful. For example, I know that sine of x1 over the square root of x2, I don't want that to appear in my solution. It's not good. Then whenever that happens, I edit that, right? So then we can edit it with a useful subtree, right? So for this, we need to have a hard rules for detecting useless functions. For example, replace x2 times sine of x3. For example, I never want to have that. Gets replaced by x2 times x3. Usually when I say useless functions, for useless functions, I don't care about the terminal node, right? So x2 sine x3 is bad. x1 sine x3 is also bad. The terminal node, the variable is not important. The expression is, I'm saying that the expression is useless for me. Something sine something is useless. So I replace it with that first thing times the second thing. Yes. No, that's what I'm saying. The question is, how do you know that you will cover all of the variables in the terminal nodes? I said you might not. Who said I want that? My terminal nodes just are a subset of my variables. They might have, my function might use all of the features or a subset of features. When, assume I said it once, assume I solve this genetic programming and at the end it gives me some solution with only a few features and excludes other features. When a feature is excluded, it basically means that that feature was not important for predicting that output. Basically, we are doing some kind of feature selection at the same time. We're selecting important features too. Yes, who said that all the features are important? Exactly, one part of the machine learning and pattern recognition is called feature engineering. One part of feature engineering is feature selection, right? Feature selection says that not all features are equally important. We can sort the importance of the features and get rid of some of the features. Again, if our best solution says that one of the features is not important, it means that you can test it at home. Assume that one feature is not important in my solution, then calculate the mutual information between that feature and the label. It must be low. Okay. So, yeah, building block operators is another way to do mutation. How? We say if we have a list of correct and useful building blocks or subtrees of operators, we can replace a subtree from the tree with a building block of operators, right? Sometimes I have good, in the previous one, I knew that some of them are bad. Some sub-expressions are bad. Here, I know some sub-expressions are good, and I sometimes use them for mutation, right? For example, I know sine of x, sine of one of the variables times tangent of the another variable is good. Sometimes I replace a subtree with sine times tangent, right? Something like that. So, in other words, what do these mutations do? It gives the user freedom to interfere in the solution. The user says, I'm willing to see sine over tangent in my solution. I'm willing. So I put it as a building block. So I use that a lot in my mutation. And probably my final solution will have that as a sub-expression, right? So it gives you a chance to interfere to the solution. Note that there is also a variant of genetic programming named building block genetic programming, see reference 2, which makes the trees from the building blocks or subtrees from scratch. So this variant of genetic programming doesn't grow the trees randomly. It just puts the building blocks together. Okay? in this variant, in this specific variant, the user says, I want the solution to be a combination of these expressions. Right? Very cool, very cool. When I learned this algorithm, I think it was 7 years ago. I was dancing because of excitement. I was so excited about this algorithm. I think it's very cool. Okay. Now the algorithm of genetic programming. So, of course, as the input, we have truth table. We have terminal set. We have function set. We have semantic rules. The truth table is also called dataset, right? And the dataset has both features and labels. So first off, we initialize the chromosomes or trees, tree structures. I denote them by Ti, where I goes from 1 to n. N here is the number of trees. Okay. Now I have a loop for every tree, T1 to Tn. What do I do? Initially, I generate the tree randomly with some maximum depth, lambda and p. Lambda was the parameter of the Poisson distribution, and p was a probability for whether being a function node or a terminal node. It gives me Ti as initial tree, right? So I will have n initial trees, n chromosomes. Then evaluate the cost of the tree Ti as I explained, right? Then you check which of the trees is the best. So you can, when you have a bunch of costs, you can see which cost is the best one, right? Then you capture best cost and best solution. You save them. Now initialization is over. Now let's go to the actual loop of the algorithm. So while not converged, not terminated, right? Then for what do we do? For every tree, we evaluate the cost. So for every tree, we evaluate the cost. If one of the trees has better cost than the best cost so far, we update the best cost so far and the best solution so far. Afterwards, we do the natural selection, right? For natural selection, what can we do? Any method for natural selection that we introduce for genetic algorithm can be used, right? Such as roulette wheel. Do you remember? Proportional selection, elite selection, elitism selection, anything, right? And they had pros and cons each, right? So we do natural selection, then crossover, we transplant the good parents, right? Then we do the mutation of the trees. And we do it iteratively until termination. And then finally, we return the best tree. And the best tree is the best function expression that we could find, right? There might be a better, but we couldn't find in these many iterations, right? I told you once, meteoristic optimization always says, this is the best that I could find. I don't guarantee that this is the best. Yes. How many trees? Always they're in meteoristic optimization, always is a trade-off. For population-based meteoristic algorithms, PSO is population-based, genetic algorithm is population-based, genetic programming is population-based. For population-based meteoristic optimization algorithms, there is always a trade-off between the number of population and the speed, because and this computation. The more population you have, the more computation you have, the less speed you have, right? And also, the more population you have, the better you search the landscape, the better you search your optimization landscape.
Yeah, the first statements, we define the best cost and the best solution, and then we go to the while loop, where we do another if statements.
Yes. So
if statements only select one tree, so one TI value.
No. So we have a bunch of parents, right? Selected by natural selection. Then I have crossover between pairs of the parents, right? Then I will have a bunch of offsprings. Then some of them will die. Then I will have the best parents and the best offsprings. Then I go to the, I will have mutation also. Then I go to the next generation. Then they become, then I do the natural selection among them. They become the parents of the next generation. Okay. Very cool, right? Very cool. By the way, you can take this idea of fitting function and do it in another way and publish a paper. Right? The idea itself is very novel. Who said that you need to do it by crossover and mutation and do it in another way and publish a paper? Right? Acknowledgements. Some slides of this slide deck are inspired by the teachings of Professor Saeed Sharifian at the Amir Kabir University of Technology, Department of Electrical Engineering in Iran. Okay, the references. So I think these were the main, the original papers. So it was proposed in 1985, a representation for the adaptive generation of simple sequential programs. Also, this one, what was this? Reference to is the building block genetic programming. So semantic building blocks in genetic programming, published in 2008. Okay. What time is it? Let's have a break, if you agree, and come back at 8:20. 8:20, yeah. Okay, let's continue. So we saw a very beautiful algorithm, which was genetic programming. Just two more things. Let me tell you very fast. That genetic programming, as we said it several times, does feature selection implicitly, right, and intelligently, right, intelligently. So in itself, it kind of does feature selection. By the way, what is feature selection? In machine learning, we have, in pre-processing of machine learning, we have feature engineering, which can be divided into feature selection and feature extraction. What is the difference between these two? So feature selection selects a subset of features and gets rid of some of them, right? It selects features, a subset. However, feature extraction transforms all of the features to a less number of features by some transformation. An example of feature extraction is PCA, okay? But feature selection selects the feature. And for feature selection in machine learning, for example, they do what? At least there are two categories of feature selection algorithms. One of them is wrapper methods. The other one is filter methods. Wrapper method, I think, is the first thing which comes to your mind for feature selection. What does it do? So you have, for example, some classifier, right? You have some classifier regress or something, right? Then you have your feature selection as a pre-processing. Of course, you can select some features and see the performance of classifier, right? So you see which features give you better performance, right? This is a wrapper method. Why? Because it wraps itself around the classifier, the machine learning model, right? But filter methods, what do? They don't care about the machine learning model. They only care about the features statistically. How? Again, they can be broken into two ways, two approaches. One approach is that I don't care about the label. I calculate the mutual information between the features. If two features have high mutual information, it means they are redundant. They're very similar to each other. So remove one of them, right? If you calculate the correlation or mutual information, or such as correlate, you calculate the correlation of features. If two features are correlated with each other, it means that they are redundant and you can get rid of one of them. The other way around, the second approach is that you calculate the correlation or mutual information between the feature and the label. In this case, you want higher mutual information or correlation. The higher the correlation of feature and the label, the better that feature is, right? Because it has more impact on that label. It is more similar to that label. Right? So these are the feature selection algorithms in machine learning, but I'm saying that genetic programming performs feature selection implicitly in itself by using some of the features as its terminal nodes, and it might use one feature twice or several times, right? Also, the idea, by the way, if it uses a feature, several times, what does it mean? That feature is very important, right? Because it has been used several times for predicting the label. Also, the idea of genetic programming itself can be implemented by other algorithms, as I said. The idea is also novel. Okay, let's move on to the next algorithm. We have some short algorithms. The description of them is short. One of them is evolutionary programming. Right. Okay. First off, let me tell you about evolutionary algorithms. Evolutionary algorithms. So, whatever algorithm that you have, which uses evolution, the idea of evolution, there are evolutionary algorithms. For example, genetic algorithm, genetic programming. We have two other, at least, methods which we are going to introduce. One of them is evolutionary programming. The other one is differential programming. Differential evolution or differential evolution, sorry. I got confused. Okay, so all of these have the idea of evolution in them. We call them evolutionary algorithms. Okay, so don't confuse evolutionary programming and evolutionary algorithm. Evolutionary programming is one of the evolutionary algorithms. It is one of the initial evolutionary algorithms. It was invented by Lawrence Fogel while serving at the National Science Foundation in 1960. So it's a bit old. Okay. So evolutionary, recall that genetic algorithm, we introduced it in the previous session. Genetic algorithm which has both crossover and mutation. Do you remember? It had both crossover and mutation. Evolutionary programming has only mutation. It doesn't have crossover. And also its mutation is a specific type of mutation. So it has at least two differences. One of them, it has only mutation and no crossover. And its mutation is also a specific type of mutation. So a specific type of mutation. It updates the candidate solutions by mutation. So we have a bunch of, initially we have random candidate solutions and they are updated by some mutation and no crossover. So the initially candidate solutions are randomly initialized in the optimization landscape. Also, optionally, in later iterations, we can have natural selection too. It's optional, right? So some of the best candidate solutions can be selected by natural selection. Again, I emphasize it's optional among the candidate solutions before and after mutations, right? So we do natural selection optionally and then mutation. Again, natural selection optionally, then mutation. We can use any natural selection technique that we discussed for genetic algorithms, right? So this is the formulation of evolutionary programming. This is a mutation in evolutionary programming. The update of a selected candidate solution Xi, and we know that the candidate solution is a vector or matrix, whatever. Here is a vector, d-dimensional vector, right? And Xi is the ith candidate solution because I have several candidate solutions, right? I might have several. Xi is updated in this way. Xi is Xi plus delta Xi. Delta Xi is the update. But what is delta Xi is defined in this way. Delta Xi is eta, is defined as eta some function phi with some parameter sigma. Okay, I'm gonna explain this to you, what these are. So eta is called a scaling factor, also called noise factor. Phi is a function, and that's called scaling function. Scaling function. Sigma is a strategy parameter. So these are the names of these three things. Okay. Scaling factor or noise factor, a scaling function, and strategy parameter. So if I have the xi here, for example, with delta xi is just a vector, right? For updating xi. So the next xi will be here in the next iteration. Usually the change delta xi is large in initial iterations because initially we want to explore more, right? But later we want to exploit more. Therefore, delta xi will be smaller. So initially for exploration, delta xi is large and gradually it gets smaller to have exploitation. The larger the scaling factor eta, the more exploration I have, because the larger the eta, the larger the delta x, the more exploration. Likewise, the smaller the eta, the smaller delta x, the less the more the exploitation. So yes, therefore the scaling factor eta can be larger in initial iterations, and again that also can be adapted and decremented gradually to have more exploitation later, right? Now let's talk about eta. So each part, let's talk about that. Eta. Eta was the scaling factor or noise factor, right? So it's a stochastic variable. First off, it's random. It's not deterministic. It's stochastic. It is random. And can be sampled. You know the difference of stochastic and deterministic, right? If you don't know that, that's nothing complicated. Deterministic means it's not random. Stochastic means it's random. Okay. And it can be sampled from various distributions. So because it's random, so I can have various distributions and I can sample from those distributions, such as uniform distribution. So for example, I have some eta mean and eta max, some range for eta, and I can randomly sample from this continuous uniform distribution between eta mean and eta max, right? Another way to do that, to draw that, is from Gaussian distribution. Eta is a scalar, right? Therefore, it's a univariate Gaussian distribution with mean 0 and variance sigma squared. Why should the mean be 0? Yeah, because xi is, we are updating it with delta xi. We don't want to change the mean. So what do I mean? It should be started from xi itself, not xi plus some mean. Did you understand? Otherwise, for example, this is xi, then I will start from here, where this is mean. I shouldn't have something like this, right? Or I can use Cauchy distribution. You understand what I'm doing, right? In addition to teaching you the algorithms, I'm teaching you some other things in statistics, in other fields of science, right? I'm teaching, it's a multidisciplinary course. Okay, so Cauchy distribution is another one. This is a continuous distribution. It's this, defined as this: 1 over pi, the pi number, the times 1 plus eta squared. Eta is a random variable. I think it's a standard Cauchy, so we can have a bit different Cauchy distribution too. Also, I don't know if you have heard of a student T distribution. Have you heard of TSNE or TSNE in machine learning? If not, just Google it. TSNE, okay? TSNE or TSNE is used for data visualization in machine learning. And TSNE uses a student T distribution, hence the name TSNE. TSNE, a student. Student T distribution is a complicated distribution. One of its special cases is Cauchy distribution. And the original TSNE, which people usually use in machine learning, is using Cauchy distribution. So maybe it's better to call it Cauchy SME rather than T. Okay. By the way, do you know why they call it a student T distribution? Because the author of the paper proposing that distribution named himself student as his nickname. He didn't put his actual name on the paper. We don't know why. Okay, so the author's name was student. That's the reason. And I think he wasn't a student at that time. I think he was a professor, but he named himself a student. But okay, and we know that it was he because we know who he was. A static scaling function is we can have. So the scaling factor is over this slide. Now let's go to the next thing. The function, the scaling function. So the scaling function can have multiple choices, right? For example, we can have a static scaling function like this. So phi of sigma is some parameter of phi, can be, or some input of phi, can be alpha sigma, where alpha is a constant scale. Or it can be a dynamic scaling function. For example, it can be a function of the iteration index and sigma. So it is a function of sigma, of course, because sigma is the input. Also, it can be adapted by iteration index. So you understand, right? This can be a function of both iteration index and sigma. It can be self-adaptive scaling function. According to the error, it can adjust itself. For example, depending on whether the cost is getting better or worse, it adapts itself. Right? And as you see, evolutionary programming is a family of methods. Depending on what you choose for phi, it becomes one of the variants of evolutionary program. Right? The simplest one is the static scaling function. Now let's talk about the sigma itself. The third thing. What was that? Sigma was the strategy parameter. In general, the strategy parameter can be a function applied on the elements of each candidate solution differently. So because each candidate solution is a vector, has some elements, and sigma can be applied, can be a function which is applied on the elements of this vector, right? Differently. So the strategy parameter for the jth dimension of the ith condition solution, we can write it in this way. So sigma can be defined as sigma ij, because for every dimension of every candidate solution, this function might be different, right? So sigma ij applied on the feature j of the candidate I, and also it's a function of iteration index. T is the iteration index, right? So the strategy parameter can be, we have also multiple ways to choose the strategy parameter. One of them is a static strategy parameter. So sigma ijt can be sigma ij. It means that it's not a function of iteration index. If you let it be fixed across the whole iterations, then it becomes static. And in practice, we have seen that it's not very good. Okay. Another one is dynamic strategy parameter. So sigma ij t, in this case, in this specific case, it is equal to sigma it. It means that what do I mean by this equation? It means that I behave all of the features equivalently. So I don't care about j. Okay. I only apply the whole sigma on the vector. So it's a function of xi, the candidate solution. Xi is the ith candidate solution, and f of xi is the cost function of the xi. So basically, in this case, in equation 9, sigma is the cost of candidate solution. Okay? Did you understand? And you will see why it makes sense. So it makes sense why, as the update sigma will be smaller if the cost is small, as we need to exploit there rather than exploring. So because the larger the sigma, the more jump I have. Okay, the larger the sigma, the more jump I have. Do you agree that if the cost is small, it means that I should search there more, I should exploit there more. Therefore, my jump should be small. So let me set sigma to be the cost value at that point. If the cost is small, sigma is also small, my jump is small, so I exploit. If cost is large, my sigma is large, my jump is large, I explore rather than exploitation. Okay. But it has a flaw. Its flaw is that we are using absolute cost and not the relative cost value, right? Whenever we use the absolute cost, some problems might occur, right? It's better to use it relatively. For example, also in proportional selection in genetic algorithm, we use relative costs, right? In Rowlett-Will and these things. So we can also use any increasing monotonic function of f, for example, g of f of x. Why should it be increasing? Because the larger the cost, the larger the sigma should become, and the more jump I should have, right? So, as I said, its flaw was using absolute cost. Now we can use relatively dynamic strategy parameter. Where we use this? How is it different? It has absolute value of f of xi minus f star, where the f star is the best or smallest cost value found so far. Okay, so basically it means that for the best, if xi is exactly at the best, is the best candidate solution found so far, its sigma becomes 0. So I shouldn't jump at all. I should be there, right? Or I can have plus some alpha 2. Then it means that for the best candidate solution, I want to jump only alpha value, and where alpha is a small number. We can also specify the direction of movement or update to be toward the best solution found so far, right? So I can say that I want my delta xi to be toward the best solution found so far. So these are the variants of the algorithm that I'm telling you. For this, we can multiply this direction that we just showed, that we just saw in equation 10. We can multiply this direction by any of the above mentioned update amounts. For example, I can use this. What is this? What is this direction? X star minus xi. That's the vector connecting xi to x star. X star is the best found solution, the best solution found so far, or the best candidate solution found so far. Okay, and we know that x star minus xi is this vector. Now I can multiply this with various sigmas that I had in the previous options. For example, I can say sigma is some scalar between 0 and 1 times this vector. Why should it be between 0 and 1? Because I don't want to pass that point. If it is between 0 and 1, it means that any of the points in between xi and x star. If you want to pass, you can set it be larger than 1. Of course, it shouldn't be negative, because not only don't I get close to the x star, but also I get farther from that, right? I shouldn't go the opposite way. Also, we can say this direction times this. What is this? F of xi minus f star over f of xi plus f star. We know that this is between 0 and 1 always, right? F star is the best cost found so far. Is it unclear? Because you are looking in this some weird way. Is it unclear or clear? So I'm giving you different options for how we can choose these. As you see, it's a family of algorithms. And variants, just giving you a list of the variants, not going into the details. So I just talked about the three main components of the evolutionary programming, but we can have also famous variants based on which scaling factor, scaling function, and a strategy parameter we choose. We can have various variants of evolutionary programming. Some of the well-known variants are these. Classical evolutionary programming, it was proposed in 1960. References 1 and 2, right? Fast evolutionary programming, 1996. Accelerated evolutionary programming, 1996. Exponential evolutionary programming, 2005 and 2006. Momentum evolutionary programming, it was proposed in 2012. Can you guess what it is doing? It has a momentum term too, right? Do you remember momentum term in PSO, particle swarm optimization? If we use momentum term with evolutionary programming, with that update that we had, this was the update, right? This was the update. If I say my current update is this plus some beta, the previous update. This is the momentum term. This is the momentum term, right? So I have a log of my previous delta X. I'm using that. And momentum dampens the oscillation, right? It helps us not to have much oscillation. The algorithm of evolutionary programming is this. Initialize the candidate solution, x1 to xn. We have n candidate solutions. Randomly, we initialize them in the optimization landscape. Then while not converted or not terminated, for each candidate solution, xi, we update it, we mutate that, right? Then if better cost is found, we update the solution. Also, optionally, we can do natural selection. And we repeat it until we find the best solution, and then we return the best solution at the end. Understood? So all of the variants are talking about the choices of eta, phi, and sigma, which we discussed. I told you some of the options for each of them. As I said, these are short algorithms. So acknowledgement, some slides of this slide deck are inspired by teachings of Professor Said Sharifian at Amir Kabir University of Technology, Department of Electrical Engineering. These are the references. Okay. Let me go to the next algorithm. Any question? No? The next algorithm is differential evolution. Okay. So there are several names which are similar to each other but very different. Don't confuse it, for example, with differential equations. You know, these are different, right? I think you must know differential equations even better than me because you're students in mechanical engineering and see this a lot, right? Have you passed any chaos theory course? Nonlinear dynamics and chaos theory? If you have passed any course in these areas, which are hard parts of the mathematics, you have seen differential equations and partial differential equations, right? However, this is not differential equations. Don't confuse that. This is the differential evolution. Okay. So again, it's one of the evolutionary algorithms, right? So differential evolution, or DE in short, is one of the evolutionary algorithms. It was proposed in 1996 and 1997. Recall that genetic algorithm had both crossover and mutation, right? We said that evolutionary programming has only mutation. This one has both, differential evolution has both crossover and mutation, but there is a difference, I'll tell you. So there are at least two differences between differential evolution and genetic algorithm. One difference is that genetic algorithm, do you remember, it applies crossover and then does the mutation. So crossover, then mutation. So the order is different in differential evolution. We first mutate and then we crossover. Okay? You might say this difference is not big because I understand that when you are in a loop, you do crossover, then mutation, or mutation or crossover. They have the same effect because the end of this loop is the start of the next loop. I understand that. I understand. But there's another difference too, that its mutation has a specific mutation form, right? So it's not any mutation. So two differences. The order is different. Also, it has a specific types of updates, mutation and crossover. So differential evolution performs mutation and then crossover. Its mutation is also a specific form, which we'll discuss. Initially, the candidate solutions are randomly initialized in the optimization landscape, as always, right? As always. By the way, no one even asked me once that rather than a random initialization, one of you guys might want to initialize it on a grid. You can do that too. Do you understand what I mean? Consider a grid on the optimization landscape and then puts the initial candidate solutions on the grid, right? Of course, the finer the grid, the more candidate solutions you need, for example, right? Why do some people initialize by grid? Can you give me your thoughts? Why is it useful to initialize the candidate solutions by grid in the optimization landscape? Yeah.
Just it's relatively equal coverage.
Yes, thank you. To have a relatively equal coverage of the whole optimization landscape. Because when you randomly initialize, you might miss some region, right? That's also choices, different choices. So initially candidate solutions are randomly initialized or put on a. Then optional, we can select all of them. So it's optional. In later iterations, we can do natural selection. Either we select all of them or we do natural selection. Okay, it's optional. And we can use any natural selection technique which we discussed for genetic algorithm. Then mutation is performed. Okay. Afterwards, crossover is performed. So we have crossover. We have mutation and then crossover, not crossover and then mutation. So we have crossover, and any crossover method that we talked about in genetic algorithm can be used. So now you understand why genetic algorithms, like the lecture of genetic algorithm was very important. This idea is used a lot in different algorithms, all right? So if both parent, let's have a discussion here. If both parents are mutated, because here we are doing crossover after mutation, in contrast to, you tell me, in contrast to genetic algorithm. In genetic algorithm, we cross over and then mutate, right? Here, we mutate and then cross over. Therefore, parents might be muted or not, right? Here, parents might be muted or not. Because we don't mutate everything, every candidate solution. We mutate some of them. Parents might be muted or not. Now we have several cases. Either both parents are muted, or one of the parents is muted, or none of them is muted. If both are muted, what happens? If both are muted, both are changed, it makes the child too much muted. Because mutation effect will be twice on the child, right? If both parents are muted, the child will be muted twice, kind of. We don't want to have that. The child will be very random this time. Okay, so that's not a good. If none of the parents are muted, then what happened? Then it raises a philosophical question. Why did we mute at all? Why did we perform mutation at all? If none of them are muted. So let one of them be muted and let one of the parents be not muted. So we select one of the parents from the muted ones and the other one from non-muted ones. Understood? Okay. The mutation of a candidate solution xi is usually in this form. So do you remember I told you that the mutation in differential evolution is a specific form, and this is the form of mutation. Xi is x, some x plus eta xi1 minus xi2. Note that this is not xi. This is some x, and different variants define this x differently. Okay. I think so far you have understood that whenever I introduce an algorithm to you, I introduce different variants of it to you. Okay, so x might be something, some point in the space, plus eta xi1 minus xi2, and xi1 and xi2 also might be some 2 points, right? So we have at least 3 options, xi1 and xi2 to have different variants. And eta is also a hyperparameter, right? Eta is called the scaling factor. And x here is the starting point for mutation, because this is a mutation, right? This x is a starting point for the mutation, for that xi. Okay, xi1 and xi2 can be either random points in the space, because in mutation we need to have randomness, right? Can be either random points in the space, or corresponding to xi, or 2 best solutions found so far. Of course, if you choose xi1 and xi2, you explore more. To be random, you explore more. If xi1 and xi2 are the 2 best found solutions, you exploit more. So it's a trade-off between exploration and exploitation for choosing xi1 and xi2. Agree? This is an example. So, for example, I set x to be some starting point, and I will tell you options for that. Okay, and xi1 and xi2 are these 2 points, and they can be either the the 2 best found so far solutions, or 2 random points. xi1 minus xi2 is the vector connecting xi2 to xi1. This is the vector. But starting at x, which is here, I use this vector to update this. So this will be my next xi. Right? Of course, if all 3 xi1 and xi2 are random, then my next xi will not be related to my previous xi at all. Agree? Because everything will be random. That might be good for exploration, actually. Right? Later attempts of differential evolution changed this equation to this. What did they do? They used a bunch of points, a bunch of pairs, rather than 1 pair, xi1 and xi2. The later variants of differential evolution use p pairs, a set of paired points per mutation of a candidate solution. Understood? I have p pairs. xij1 minus xij2. J is the index of pair. I means that they are corresponded to candidate solution xi. So don't confuse that. I is for the candidate solution. I'm corresponding to ith candidate solution. J is a jth pair. And 1 and 2 is the 1 and 2 in the pair. Right? So this equation we can use. P is the number of pairs per mutation. Okay. An example of this illustration is this. So consider 2 pairs. This is one of the pairs whose vector is this. This is another pair whose vector is this. We have a linear combination of them, right? So we have a linear combination of these 2 vectors. Here we have two pairs. If we had p pairs, we would have a linear combination of p vectors. Then my next xi will be here. Okay. Now let's discuss eta, which was the scaling factor. Of course, the larger the scaling factor eta, the more exploration I have, because the larger update I have. The smaller the eta, the less jump I will have, therefore more exploitation I will have. Agree? So again, we can initialize by larger eta and decrement eta gradually to have more exploration initially and more exploitation later. Now, as I said, differential evolution has variants, right? We can denote the variants in this way. They usually denoted in this way in literature. X/Y/Z. So what do I mean? The first one, which is X, stands for the starting point of the mutation. What do we use as the X in this equation, 2 or 1? What do we use for X, right? Also, Y, which is the second one, is for the number of pairs per mutation. How many pairs do I use? Z, the third one, is for the crossover method. What method do I use for crossover? So as you see, we have a lot of variants. Some of the most well-known variants of differential evolution are these. Xi1Z. What do I mean? This means that Xi means that what? My starting point is my current candidate solution. So starting from the current solution, current Xi. 1 means I use 1 pair, and this pair can be either random or best solution found so far. Best solutions, sorry, because it's a pair. What do I mean by best solutions? I mean, you can sort the best solutions found so far to take the top 2, for example. And any crossover method. So that's why I have put Z, any crossover method. Right. We saw a lot of crossover methods in genetic algorithm lecture, right? So basically its formula is this. Xi equals Xi, which means the previous Xi, plus eta Xi1 minus Xi2. So here, in the figure, X became Xi. Right? XIPZ. What do I mean by this? Starting from the current solution, because of Xi, but having P pairs, and these P pairs can be either random or best solutions found so far, or you can take some of the pairs from the best found solutions so far and some of them random to have a combination of exploration and exploitation. You can see that you can have various variants of the algorithm and any crossover method. So its formula is this. Its figure is very similar to what we had, but this X is Xi this time. Another variant is X star 1Z. What do I mean? Let the X, which was the starting point, be the best solution found so far. What do I mean by this? I mean that when I want to mutate, let them be mutated around the best solution found so far. So let me search around on my best solution. Of course, it is for exploitation, right? It's not for exploration. Also, you shouldn't stick to one of the variants from the start until the end. You might switch. Initially, in initial iterations, you might have Xi1Z, for example, XIPZ, and to have more exploration. Later, you switch to the variant of X star 1Z. So you can switch between variants during optimization. Right? So it starts from the best solution found so far, 1 pair, either random or best solutions so far, and any crossover method. So the difference here is that it's X star this time. Or we can have X star PZ. So P pairs starting from X star, like this, right? This equation. Here you see these are X star. Another variant is current to best P and Z. So first off, we are using P pairs. Sorry, this is P pairs. P pairs and any crossover method. But the difference here is that it starts from a random point between the current solution and the best solution found so far, right? So let's have a kind of interpolation between where I am right now and where my best solution is found so far. You can see imitation from the PSO algorithm too, right? Kind of the backbone of idea of PSO is also repeated here. So we have this, as you see, what is this? We can implement it in two ways. Either gamma X star plus 1 minus gamma X star Xi. Gamma is between 0 and 1. What does it do? You tell me. Assume this is Xi. This is X star. How can I write the equation of the line between Xi and X star? How can we do that? We can say gamma X star plus 1 minus gamma Xi. Sweep gamma between 0 and 1. If gamma is 0, what happens? This expression becomes Xi. So I'm on the Xi. If gamma is 1, this expression becomes X star. So I'm here. If gamma is between 0 and 1, I'm somewhere in between. Right? Now I'll give you a puzzle. You tell me. What if I want to go further than this? Either further than Xi or further than X star. What is the equation? The equation is the same, but the range of gamma will change. Now let gamma be between minus infinity and infinity. Right? If gamma is negative or greater than 1, I will go further than these 2 points on this line. Right? So according to the analysis that we talked about, this is some point, based on what gamma we choose, some point between Xi and X star. Because gamma is between 0 and 1, right? And we have P pairs. Another way to show that is that this Xi plus gamma times X star minus Xi. What is that? What is this X star minus Xi? It's a vector connecting Xi to X star. It basically means that starting from Xi, go along the direction of connecting Xi to X star, but how much? With the gamma amount, where gamma is between 0 and 1. So I will end up with somewhere between Xi and X star. Right? And also have P pairs. This is the figure, for example. I have 2 pairs here. And this is X star. This is Xi. So gamma X star minus Xi is somewhere in between here. Right? So starting from here. Sorry, I think give me a second. I think the figure is better to be drawn in this way. So starting from here, I update it in this way. So my next solution will be, did you understand? Starting from here, I have these two vectors. The algorithm of differential evolution is this. Initialize the candidate solutions, Xi to Xn, while not converged, while not terminated. For each candidate solution, Xi, draw P random points in the feasibility set, right? In the feasibility set, in the domain, satisfying also the constraints. Draw P random point. And or get the P best solutions, whatever. Then update it by this. And this X might be X star, might be any solution, any starting point. Check the cost. if it is better than the best cost found so far, update the best cost found so far, and also update the best solution found so far. Then perform crossover on the between mutated and not mutated parents to generate some offsprings. Then do the natural selection. Then go to the next iteration, right? And finally return the best solution. Again, I acknowledge Professor Said Sharifian at the Amir Kabir University of Technology. Some good books on differential evolution. You can see references 3 and 4, published in 2006 and 2013. So there are books on that. Okay. Some surveys on differential evolution. These references in 2010, 2016, 2019, 2020. So we have recent surveys on them. Right. And these are the references. So as you saw, we saw some algorithms which were evolutionary algorithms based on evolution, the concept of evolution, right? And these are very important algorithms. Don't think that these are not very important. Differential evolution, evolutionary programming. The family of the evolutionary algorithms is very important. As I said, one of the categories of archive is evolution algorithms, right? In that category, you can see either the papers about neural networks or about materialistic optimization. So whatever paper which you want to find in archive, you should about materialistic optimization, you need to search in that category. Okay. Any question? No? Okay, let's move on to the next topic. I think the next topic is taboo search. Okay, taboo search. Taboo search is also short, but very interesting. Very interesting. So, taboo search is a meta algorithm. What do I mean by meta algorithm? Can you tell me? What is meta here? We see this meta in the terminology of meta heuristic too. Is it for computer? No, but why did I call meta-heuristic algorithms meta-heuristic? You are saying. Yes, so thank you. So it can use other it can be used with other algorithms. It's not itself an algorithm on its own. You use it with other algorithms. So meta-heuristic optimization said what? I don't care about your optimization problem. It can be anything. You can use me with any optimization algorithm. Here, meta algorithm means that you can use it with other algorithms. In this case, I can use it with other meta-heuristic optimization algorithms, right? I myself put one paper on archive for a meta algorithm for meta-heuristic optimization. I did it at the end of my undergrad and at the start of my master's. So it is called tree-based optimization. It's not that much very perfect, but it was one of my initial points. I think initial papers. I think it was my second paper. My first paper, both of my papers, which were initially work, were on meta-heuristic optimization. I think you can now estimate why. You can guess why. Because meta-heuristic optimization is easy. Doesn't have much mathematics, right? Initially, my knowledge was limited, right? And I tried to improve myself, but still, I'm not very knowledgeable. But at least I'm trying. But I'm saying that initially, my papers were on meta-heuristic optimization. The first one, if you go and see that, it's called Pantagruelis meta-heuristic optimization algorithm, PMSO. So it's a nature-based optimization algorithm, and it tries to imitate Gomarus, which is a creature in the Caspian Sea. Okay. If you go and see my paper, that paper, some of my figures are like cartoons. Okay. I depicted them myself. was hard, but anyways, I tried to put some math in that. But anyway, the next thing that I proposed in materialistic optimization was tree-based optimization. And its idea, I think, was also interesting. Its idea was this. I think you can guess. I can assume I have some optimization landscape. For simplicity, assume it's 2D. I can divide my optimization landscape into several parts. For example, 4 parts randomly, right? 4 parts randomly. Then every part region I can divide into sub-regions. Again, into sub-regions. And I can go to the sub-regions probabilistically, stochastically, but with what probability? With the probability of costs found in those regions. For example, I do search in this region, this region, this region, this region. I see that this region is better. So with more probability, I go into that region. And I get rid of the other regions. So I'm decreasing, I'm making my optimization landscape, my search space smaller and smaller. Stochastically, with what probability? With the probability defined by my best solutions found so far in those regions. Did you understand? You might be wondering, if I find a better solution in this region, why do I go to this region stochastically? Why don't I go to this region deterministically? There is a reason. Because if I do that, I might get stuck in the local best, right? What if the solution that I found here was good, but it was a local best? The global best might be here that I never saw, right? You might be also wondering a second question, that what if the actual global best is here, and I found it here, but probabilistically, I went in this region mistakenly, right? And I got rid of this region completely, right? So I have also an answer to this question. I do this, I repeat this for several times. I repeat the whole algorithm for several times, okay? And hopefully in one of the iterations, I can correctly go to the global best region. And also, how can I implement this division by 3? I can do that by 3, right? I can have various ways of tree. This is binary tree. I can have more branching factors, right? If I have more branching factor, then what happens? For example, I can divide in this way. In this way, right?
The binary search or like, oh,
So I can have divide my regions like this, or depending on the branching factor, I might have several things, right? And also the branching factor can be random. So you see, you have various variants. And this is a meta algorithm. Why? Because in every region, I can use any materialistic optimization search that I want. I can use genetic algorithm in the regions. I can use PSO in the regions. Interestingly, I can use various algorithms in different regions. In one region, I can use genetic algorithm, and in another region, I can use PSO. Right. So I named that algorithm tree-based optimization, a meta algorithm for materialistic optimization. And I put it on archive. Of course, it never gets published. It never got, because it was one of my initial papers. It wasn't that much strong, but you can take a look at that, and that was interesting. I think we don't have much time to go into the tablet search this time, but it's a meta algorithm. Its main idea is that whenever I see some region like this, I don't want to repeat them. So I already have seen them, right? Why do I go and do redundant search? So I put them in a list. I call it taboo list, because those are taboo and I don't want to go to them again. Okay, this is and as you see, for finding these candidate solutions, you can use any materialistic algorithm, such as PSO genetic algorithm. So it's a meta algorithm. Okay, we'll continue in the next session. Thank you. Thank you. Thank you.